Okay, so hello everyone. So welcome to our this semester's Rugged Efficient AI seminar. And today we're very glad to have the Professor Linghao from the Yale University to give us this talk about the sparse linear algebra acceleration using FPGA. And Dr. Song is an incoming assistant professor in Department of Electrical and Computer Engineering at Yale University and a postdoc researcher in the UCLA Computer Science Department. His research interests include domain-specific accelerator, computer architecture, memory-centric computing, machine learning acceleration, and FPGA prototyping and acceleration. He received his PhD in computer engineering from Duke University in 2020, master's degree from the University of Pittsburgh, and a bachelor degree from the Shanghai Jiao Tong University. He received the 2020 EDA Outstanding Dissertation Award and the 2021 Duke EC Outstanding Dissertation Award. Okay, so now let's welcome Professor Song to give us this talk.
Yes, thanks very much. Thanks, Professor Yuan, for the invitation and the introduction. So, good morning, everyone. I'm Linghao Song, a postdoc from UCLA, and I'm also an incoming assistant professor in Yale ECE department. So today I'm very happy to share our works about sparse linear algebra acceleration on high bandwidth memory FPGAs. So actually okay. So in this work, we like to use FPGAs as computing devices. So probably you may know, I mean, if you are working on FPGAs in the past several years, actually FPGAs are good for doing some prototyping, but FPGAs are not good for, I mean, use as the computing devices because of the low frequency. So next slide, yeah. So since our focus is to use FPGAs to build accelerators for deployment in real computing systems. So here we first let me show you some challenge. So because actually FPGAs are very good for architecture prototyping, but when it comes to the performance of FPGA accelerators, so for the performance modeling, we know that in a classical architecture modeling, actually the peak performance is the inverse of execution time, and then you will find that this performance is proportional to your frequency. And let me show you some, I mean, typical frequencies of some computing devices from CPUs to GPUs, ASICs to FPGAs. So here we see that actually the operating frequencies for CPUs for most of the scenarios the highest, and then it's the GPUs and ASICs, and for FPGAs they usually run at 100 to 300 megahertz, and among those four computing devices, FPGAs have the lowest operating frequencies. So is that always true that low frequency will give you low performance? So besides this performance, I mean performance modeling proportional to the frequency, here we have another, I mean performance modeling, which is the widely used roof-like model. So besides the peak performance, which is proportional to your operating frequency, in the roof-like models, there are actually three components. Besides peak performance, there are two more components. The one is the bandwidth, which is actually metrics about your memory system. And the third one is the computational intensity. Basically, the property comes from the application itself. So in roof-like model, there are two typical, I mean, applications. One is the computation bound application. So for example, suppose we have a system where the memory bandwidth is 10 GB per second, and the max performance is 200 GOPS per second. And suppose we have, I mean, 100 processing unit, and each unit can perform one operation per cycle. And suppose we are running an application and its computational intensity is 40 ops per byte. So for these applications, so the required frequency is very high because if we multiply this 40 ops per byte with your bandwidth, we will get 400 GOPS per performance, but the max performance provided by this platform is 200. So the achievable, peak performance will be 200 GOPS. And now we have 100 processing unit. So the required frequency is 2 GHz. So that means for this scenario, this computation bound application, we need to set the frequency to 2 GHz to saturate the 200 GOPS max performance provided by the platform. So in other typical application in the REFAI model is memory bound application. So we move from this point to this point. So we assume the same memory bandwidth, 10 GB per second, the same max performance provided by the platform, and the same number of processing units, and they are the same. They have the same computation capability. That is, each PU can perform 1 op per cycle. But the only thing that is different is that we are now running another application. That application, the computational intensity of that application is low. Now it's 1 op per byte. So the computational intensity changed from 40 to 1. So for this application, the required frequency is now very low, because if we multiply this 1 op per byte with the memory bandwidth, it's 10 GOPS, right? So that means for this 10 GOPS performance, the required frequency is now only 0.1 gigahertz, because now this application is bound by your memory bandwidth, not the computation. Even if we, set the frequency to a higher value, for example, 200 megahertz, from this point to this point, but your memory bandwidth will limit this data supply to your processing unit. So that means you will still achieve, here is 10 GOPS per second performance. So here in this slide, I just want to show you two, typical application provided by the REFAI model. And remember that for the memory bound application, the required frequency is low. So here comes to our opportunity. So because we like to use FPGAs as computing devices, and we know that FPGAs has a relatively low working frequency. And as my previous slide shows, that we need to focus on the sparse workload, which is memory bound. So here I give a comparison of the computational intensity for, two applications. One is ResNet 50, which is, this model is computation bound. So the computational intensity is very high, to 20 flop per byte. And the other one is called SPMV, which is memory bound. And we see that the computational intensity is less than 1, actually very low. So, we are now using FPGA as computing devices and focus on sparse workloads, but we still like to get a high performance. That means we need the platforms to have a very high memory bandwidth. And or fortunately, the recent FPGAs like the U280, they are equipped with the HBM, high bandwidth memory. So in previous like DDR FPGAs like this, we see the bandwidth is only like 77 GB per second, but now the memory bandwidth can go up to 460 GB per second. So adding all this together, the FPGA platforms, the sparse workloads, and the high bandwidth HBM memory. So now that these are all this give us these are very good for us to build, sparse accelerators on the HBM FPGAs. And now our architectural goal is to design the architecture to saturate the memory bandwidth on the high band HBM FPGAs. So for our SPM, our question. Okay, so for our sparse accelerators, we target the sparse matrix multiply SPMM and sparse matrix vector multiply SPMA. So here in this equation, to define the SPMA and SPMM, actually we can use this equation C equal to alpha A multiply B plus beta C to represent both SPMM and SPMA. So for SPMM, here A, B, C are three matrices, and A are sparse matrices, and B, C are two dense matrices. For SPMA, A is the sparse matrix, but B, C become two, dense vectors. And here are beta two scale constants. So we do, SPMM and SPMA accelerator because they are widely used in many applications like sparse deep learning, graph convolutional networks, and also many scientific computing applications. And more importantly, as Professor Yuan introduced, that the SPMM and SPMA are very fundamental in two very fundamental operators. So in the sparse processing, the first challenge we are facing with is the random off-chip memory access. So because we are processing large scale matrices and we store those matrices in off-chip memory, let me show you an example to better understand the off-chip memory access. So here on this slide, so suppose we are first processing this green 2 element. So to process this element, we need first read this element, this green 2 from the A matrices, and then we will read this column, this green column from the B matrices, and then we do the multiply, and then we will accumulate to this row in the C matrices. And next cycle, if we move to the processing of this light blue 5 element, again, we need to fetch this element from the A matrices. And then we need to read this column from B matrices. And then we need to do accumulation on this row on the C matrices. So here, So here we see that the memory access on all the 3 matrices, like on the C matrices, we are access from this one to this one. And on the B matrix, we are accessing from this column to this column. And on the C matrices, we are actually accumulating from this row to this row. So the memory access pattern on all the 3 matrices are random, and we know that they are stored in the off-chip memory. So that means this sparse processing actually generates a lot of random and off-chip memory access. So we know that random access is very inefficient, and off-chip memory access is again also very inefficient. So how can we solve this challenge? Our scheme is that we design the memory access with the partition matrices. So in the processing, we first move a block of B matrices from the off-chip memory to keep this block on chip, and then we stream in A matrices. So for every element, A element we stream from the off-chip memory, we do the reading the B column access to the on-chip memory, and then we accumulate to the C matrix, which is also stored on chip. So in this way, for the random access, we actually keep all the random access on chip, And for the off-chip memory access, we are doing the sequential and the streaming access. So here you can see we actually, with this partition scheme, the memory access in our accelerator is very efficient. So next, another challenge actually in this sparse processing is about the pipeline bubbles. So this pipeline bubbles is introduced by the floating point accumulation. We know that floating point processing cannot complete within one cycle. So here, in this example, I assume that a floating point accumulation needs 2 cycles. So in the default pipeline, we see that there is one bubble between every element. We know that pipeline bubbles will actually makes your processing time longer. So to actually efficiently use the pipeline, we introduce the auto order scheduling. The idea is actually very simple. So we just do not follow the default orders. We use an auto order scheduling. So here, for example, after we scheduling one element to the pipeline, like here, this blue 0 to the pipeline, we actually we can move some later element. For example, this red one, which do not have a conflict with a previous element in the pipeline, and then we just schedule this element that do not have conflict with the elements in the pipeline to the pipelines. So in this way, we can utilize most of the pipeline bubbles in the default pipelines, and then we can save the processing cycles. The third challenge is about the support for arbitrary problems, because we for our sparse accelerators, we like to use them we like to deploy them in a computing systems. So that means we do not we cannot rebuild a new accelerators for a new problems, because we know that building hardware accelerators will take usually takes very long, like tens of hours to build the hardware accelerators. So to support an arbitrary problem with the accelerators, by default, we can use some software schemes to decompose the very large problems into very small size and then launch the kernels. But here is the problem: is the high cost from high latencies from the host to for the the launching process from the host CPU to the accelerators. The host accelerator and CPU and accelerator latency usually like 0.1 to 0.2 milliseconds. To actually, reduce this host to accelerator latency, we move the launching process from the CPU side to the accelerator side. So the idea is that we deploy a controller at the accelerator side, and then we launch the PEs with these controllers. So in these schemes, now we have a very low latency, because for this controller to launch the PEs, the latency is usually within a few cycles, that is like tens of nanoseconds. So compare these two latencies, we get 10,000 speed up. So here comes the architecture of our sparse accelerators. So our sparse accelerator architecture is a hierarchical architecture. So it has 3 levels of hierarchy. So the first level is the PEG processing engine group. It is used for matrix blocks computation. And the second level is about the processing engine. So we use the processing engine to perform the computation on sparse and scalar and vector. And the third level is about the processing unit, which is used to perform scalar to scalar computation. And our architecture is actually memory-centric. So that means we connect one processing engine group to one memory channels. So this memory-centric design actually makes our architecture scalable. So we can, easily scale up our PEG numbers to match the memory bandwidth, a higher memory bandwidth. So another question probably you like to ask is that how low should we set the frequency to be? Since our architecture is a memory-centric design and we need to match the optimal memory bandwidth, so the matching frequency actually can be calculated using this equation. So F equal to bandwidth divided R. So the BW is your optimal memory bandwidth for the U280 FPGA. So the overall bandwidth is 460 and it has 32 channels. So we can calculate the bandwidth for each channel, use 460 divided 32. And this R is the maximum memory data width provided by the platform. So for the White's platform, this R value is 64 byte. So here we can calculate the bandwidth matching frequency for our Sparse accelerator is 225 megahertz. So this is not a very high frequency, and it can be easily achieved by the current FPGA tools. And next, so to build the SPMM and SPMV accelerators, we use HLS, high-level synthesis. So we use HLS to first describe our accelerator architectures, and then we use the winner tools, that is the White's, to transform our HLS code to the hardware. So for the SPMM accelerator, it actually takes 10 hours to convert our architecture description to the hardware. And for the SPMV accelerator, it only needs 6 hours. This process is actually very fast. So for the performance of the SPMM accelerator, we compare with K80. This is a GPU which has similar memory bandwidth. So here we see that our accelerator, our SPMM accelerator actually achieve 1.5 x throughput compared with K80 GPU. And for the energy efficiency, we actually get 6 times higher energy efficiency than the K80 GPU, and we can also support a very wide range of problems. So for the number of non-zeros, we can support up to 150 million. And for the SPMV accelerator, we compare our accelerator with, besides comparing with K80 GPU, we also compare with, 2 other FPGA accelerator, that is Lily and Sparse. So here for these 3 FPGA accelerators, they are prototyped on the same FPGAs, the U280 FPGA. So on the same FPGAs, we see that we actually can achieve up to 3 times speed up compared with 2 other, SPMV accelerators prototyped on the same FPGA. And we also get 1.71x energy efficiency compared with the 2 other SPMV accelerator. So after building the SPMM and SPMV, which is 2, basic sparse linear algebra operators, we are thinking about how to use our sparse accelerators in real-world application. So here comes to our collaboration with Ansys. So here we like to accelerate Ansys LS-DYNA. So this is the simulation software for modeling and engineering problems. So Ansys LS-DYNA they can use for many applications like for the car crash modeling, fluid dynamics, and also some material analysis. So our collaboration with Ansys start from the bottleneck analysis of Ansys LS-DYNA. So to understand the bottleneck of Ansys LS-DYNA, we first perform an end-to-end execution on CPU, and by our profiling, we find that the overall time for this Ansys LS-DYNA for this example is like 700 seconds, and the conjugate gradient solver, the CG solver, actually takes 94% of the overall execution time. So that means the Ansys LS-DYNA is a very good application for acceleration because it is good for acceleration because it has a single bottleneck, and this CG actually dominates the overall processing time. So for applications that has multiple bottlenecks, so it will be very difficult to accelerate because you need to design multiple accelerators. Now it's very good because this Ansys LS-DYNA has single bottleneck. And this CG, the bottleneck is memory bound. So that means it's very good for HBM acceleration. So the CG solver used in the LS-DYNA is the Jacobi preconditioned conjugate gradient solver. So here I show you the pseudocode of this algorithm. So this algorithm, what this algorithm is doing is actually iteratively solve this AS equal to B equation. So for this equation, we know the sparse matrix, and the right-hand side, the B vectors, and we need to find the X. So this JPCG actually iteratively refines the errors and approaches solution. And in the main body of this algorithm, the SPM way and the vector multipliers are the main operations. So to build the accelerator architecture for the JPCG, we first map the operations of this algorithm into computation units on the hardware. So from SPMA to all the dot product and the vector update units. Next, we design the memory access units. So those memory access units, the read and write modules, are used to fetch data from the off-chip, the HBM memory, and then deliver them to the on-chip module, or store the results from the on-chip module back to the off-chip memory. And we also need to deploy the control modules that include the vector control modules and a global controller to coordinate the data flows among all the on-chip modules, and also the overall execution for the accelerator. So we call our JPCG accelerator Curly Pepper. So here, you see that there are so many, hardware components and variables in the accelerator. So the one challenge is that how can we coordinate the computation and data flows in such a complex system? Our solution is that we come up with a stream-centric instruction set to solve the complex control and coordination challenge. So there are there are three types of instructions in our stream-centric instruction set. The type 1 is the vector control instructions, so which is used to control vector flows between memory modules and the computation modules. So here, to use this vector control instructions, you need to tell whether it's a read or write operations, or actually we can do simultaneously read and write. So that means you just set here to true and this write flag to true. And next, you need to tell the base address of the vector in the off-chip memory, and then the length of the vectors. And finally, we use the QID to indicate the destination module index. So because our, memory modules is connected to multiple on-chip computation units. So this QID will tell which computation modules we need to send the vector to. So type 2 is the computation instructions. So we use computation instruction to invoke the execution of computation modules. So to use the computation instructions, so what we need to do is to tell the length of the vectors and to set the alpha value, which is the scalar constant, because in the vector update, we will use a scalar constant, and also we will use a QID to tell the destination, the index of the destination modules to send the vector to. And the third one is about the memory instructions. So we use these memory instructions to read and write vectors from or to the HBM channels. So to use the memory instructions, we need to tell whether this is read or write operations, and the base address and the length of the vectors. So here is the processing model for our stream-centric instruction set architecture. So in this architecture, besides those modules and the streams connect to the modules, we have a global controllers. So this global controller will issue computation instructions to computation modules like M1, M2, and also this global controller will issue vector control instructions to the vector control modules. And then this vector control module will issue memory instructions to the memory modules. So using this global controller and those three types of instructions, so we can coordinate the flows and the controls of the whole oscillator. So our stream-centric instruction set actually makes the control very efficient and the controller code very elegant. So here, let me show you two examples. For example, if we like to do the M3, which is used to update X. So what we need to do is that we just issue a X vector control instruction for the X vectors. And because here, besides X, we also need to read in the P vectors. So we just issue another vector control instruction to the P, and then we issue a computation instruction to these modules to update this X. And then finally, we will use a response signal to serve as a barrier because we need to keep the content that the X in the memory consistent for different modules. So another optimization we performed for this conjugating star is the mixed precision SPM way, because by default, the double floating point, the FP64 is required. We are thinking about using FP32 in our accelerators because FP32 has lower bandwidth requirement. But if we compare the accuracy, we know that the FP64 is better. So can we achieve FP64 similar accuracy with lower bandwidth requirement? So we first explored the three mixed precision configuration for the SPM way, that is for the A matrix, the X vector and the Y vectors. So in the default setting, all the A, X, and Y is configured with FP34, and for our mixed precision version 1, we set all all three of them to FP32. But for the other two versions, the V2 and the V3, we actually keep the A matrix to FP32, but we configure FP64 for the X and Y vectors. So here's the numerical result of the three mixed precision and the default FP64 precision on three matrices. So here we see that actually the mixed V3, the third version, actually has the best numerical results. So we actually configure this mixed V3, so where we set the A matrix to FP32 and the X and Y vectors to FP64 as the precision configuration for our accelerators. To evaluate our conjugating solvers, we actually configure with three CG solutions. So the XCG solver, this is the CG solver provided by Xilinx, and the Serpent CG is one of our previous work, and the NVIDIA A100, we use NVIDIA A100 to for the GPU CG solver. So for this GPU CG solver, we use actually CUDA 11 version 11 with Sparse and Sparse, and for those three, FPGA accelerators, the XCG, Serpent CG, and our CG solver is Calipepla. We prototype all three of them on U280 FPGAs with the Xilinx YTX version 2022.1, and for the Serpent CG and the XCG solver, the precision is the default FP64, and for our Calipepla, the precision is the mixed precision scheme. So here are the matrices in our evaluation. So we evaluate at 36 or large-scale matrices, and let me show you the overall result of our evaluation. So for the throughput, actually, if we look at the maximal, the highest performance throughput, of course, is the A100, because the A100 GPU actually has the highest bandwidth. Here we can see the bandwidth of the A100 is almost 5 times compared with the FPGAs. But our accelerator, the Calipepla, is not like 5 times slower than the A100 GPU. We actually achieve almost 70% of the performance, the geometric performance compared to the A100. That is because the power of the spatialized architecture. And for the power efficiency, because we like to deploy the accelerators in cloud, so actually we need to care about the power and the energy efficiency. So we see that we have our solution has the highest energy efficiency. That is even compared to Xilinx solution, we are 3 times better. And compared with the A100 GPU, we are almost 4 times better in terms of the energy efficiency. So after evaluate the conjugating solver itself, the kernel itself, we actually integrate our accelerators into Ansys LS-DYNA flow. So we evaluate on this example. This is a UK atomic weapons establishment benchmark. and we compare the 4 different platforms. P1 is the baseline with 1 CPU, and P2 is a platform with 8 MPI ranks, so CPUs, and P3 is the platform with 1 A100 GPU, and P4 is the platform with 1 U280 FPGA with our accelerators. So for the speed up, actually compared to the baseline, the 1 CPU version, we are 9 times faster. And compared to the A100 GPU version, we achieved 74% of the performance of the GPU. And for the energy efficiency, energy consumption, we consume the lowest energy. And if we compare the cost, I mean, for all the 3 accelerated computing platforms, the cost of our platform is the lowest. And on the right-hand side, I show you the terminal output of the Ansys LS-DYNA. So here it says that this Ansys LS-DYNA is using the U280 FPGA to execute the CG solver. So for the SPMM accelerator, SPMW accelerator, our conjugating solvers, we open source the code, and they are now available on GitHub. So if you like to use our accelerators, you can just download and follow the flows to reproduce our results. So as a conclusion, because the focus of our accelerator is sparse linear algebra, and sparse linear algebra has low computation intensity. They are memory bound, so they require actually relatively low working frequency, which is good for FPGAs. And the latest FPGAs, they have the the high bandwidth bandwidth memory, which provide high memory bandwidth. So this is very good to customize the memory-centric processing architectures, and this enable us to get high performance for the sparse workloads. So in our work, we illustrated the potential of HBM FPGA accelerators for high performance computing with our sparse accelerators, SPMM, SPMW, and the conjugating solvers. And we also demonstrate the integration and the deployment of accelerators into a real world industry software, Ansys LS-DYNA. So actually, I would like to thank my collaborators and those funding agencies. And I also list the reference in my slides here. And thank you very much. I'm happy to take questions.
Thank you, Linghao, so for a wonderful talk. And I have several questions, but I will first to leave the opportunities to the audience. So any questions from the audience? So you can either unmute yourself or you can input your questions in the chat box. I think maybe I can go first. So Linghao, I noticed that, so actually in your comparison with the A100, so there's one table there. And yeah. So here for the throughput, so for the the peak here, it has very high value. So I was wondering, so what is the difference between the peak and the max?
Oh, peak is actually the performance achieved by the performance from the computation units of that platform.
You mean it's kind of it is the potential maximum
Right. All the hardware, yeah. And the max performance is the achieved highest performance on the application.
So
for
here,
the application.
From this table, we can see that actually the L100 is largely underutilized.
Only right. So here there's another metrics about the fractional peak. So this is about the how many computations you have utilized. For example, for A100, you just yeah, less than 1% of the overall computing powers are used.
Yeah. So then actually, so as including your approach and another XCG solver, so the utilization is also just like 4 or 10%. So I was what is the reason? It's because the workload is still not large enough, so or some other reasons.
Yeah, I think actually the reason is that one of the reasons is that because the workload is large, so and also the memory access is very random, so that means it's very difficult that you to fully utilize the hardware potential.
Okay, I see.
Yeah.
Okay. So what is kind of the largest the metric size you use?
So here you see the largest matrix size we evaluate on for the CG solver is this matrix. So for this matrix, the row number is over 1.5 million, and the number of non-zeros is over 100 million.
Okay.
Yeah, they are very large matrix.
Okay, I see. I have some following questions. Questions from the audience? I think there's one question in the chat box. Can you see that?
Oh, I see. And so one question is, can FPGA-based accelerator accommodate different types of sparse matrix on block diagonal since changing the algorithm leads to changing the architecture? Yeah, I think that actually this is a very good question. So what our scheme is that we can actually we have a fixed data format for those matrices. So that means for different types of the sparse matrices, you just need to convert the matrix type to match our defined data format, and then you can execute that matrix on our accelerators.
So actually, I have some kind of related questions following this one. So, do you need to change your or partially reconfigure your architecture for the better support those more kind of structured or semi-structured sparse matrix?
Yeah, actually, to execute the arbitrary matrix on our accelerator, we do not need to reconfigure the architecture. But if you like to get a better performance, I would suggest you to, do some architecture modification.
For example, you can like to add another module that like the adapter, just at side of your main data path.
Yeah. That's a very good question.
Collection scheme.
So here you see, because we have a modularized architecture design, and also we have this stream-centric instruction set architecture. So that means if you like to add some your customized architectures, it's very easy to just design a module and then add to our architecture.
Okay. Some other questions from the audience? So then actually, I have another follow-up question. Yeah.
Sure.
So from the perspective of the architecture level, so I know that for the sparse matrix multiplication and matrix vector multiplication, maybe so the sparsity may varies a lot, and the computing pattern may be a little different. So I was wondering, so in your research works for this one, so have you ever considered about the different types of data flow is a fact. So about the mapping space, the choice of your mapping strategy. We know that like in the deep learning accelerator, we have like the row stationary, weight stationary, and so on, right? And you can choose like you want to use the outer product or use the inner product for those sparse. We have already seen a lot of works in the R conferences. So I was wondering, so in your work, especially in the context of the FPGA implementations, so whether there's some kind of such kind of different design choices may have some kind of we need to reconsider them right now, considering the constraints of the FPGA devices.
Mm-hmm. Yeah. So I mean, so I know actually from the a perspective about the deep learning accelerators, there are a lot of like mapping schemes, either about the input weight or output stationary scheme, right? So, and also I know there's a lot of works which explore different mapping scheme. But for our, sparse accelerators, the stationary scheme is something like a output stationary scheme, but it is not because thinking about it, if you are doing the sparse matrix to vector multiply, the vector size is actually much smaller than the matrix size. So that means it will be very good to just cache part of the matrix vector on chip, and then we streaming the large size matrices, sparse matrix from the optic memory, and then we just do the random access to these small size vectors.
Okay, so that means
Yeah.
that the selection or your selection of data flow actually you consider about the kind of the property of the workload.
Right.
Okay, that's right. I think we have some other, I think two questions in the chat box.
No, that's a very good question. So the question is that what role does rapid stream play in the layout architecture? What main benefits did it allow over traditional layout design flow? So actually when we are designing our accelerators, the very early version of our accelerators are using the Vivado design flows. We do not use rapid stream, autobridge, or topper, and just with the traditional Vivado flow, we find that it's very difficult to scale up. Make the accelerators larger, because after we deploy more modules on the FPGAs, we find that the traditional Vivado flow will cause the routing very congested. So that means the traditional flows will be very difficult to make the frequency higher, or just the large accelerator just failed placed and routing with the traditional flows. So with the rapid stream, is the autobridge tool and the topper tools. So we can do some coarse-grained flow planning with in the HLS levels. So that makes the place and route much easier when we are doing the back end design. After we're using the autobridge and topper, so that makes the place and route much easier with the Vivado flows. Is that clear? So for the rapid stream, so rapid stream does not completely, replace the traditional Vivado flow. It's just we use the autobridge and the topper as some, front end tools, and then we use the generated, the Excel files to the traditional Vivado flow to do the place and route. So Vivado is still served as the back end tool in our design.
I think there's another questions.
Other question? Oh, I see there's the FPGA with HBM models. So I see the question from Yu Gong. There's two questions. The first one is about is the performance bottleneck still communication with the CPU or PCIe? So for single accelerator design, the bottleneck is at the HBM actually, because we only need to move data from CPU side to FPGA once. But for if you like to scale up to multiple, FPGAs, then the PCIe becomes the bottleneck. And next question is it a good idea to build a heterogeneous system with GPU computation, CXL device? Of course, because CXL AutoCAD actually enables us to, efficiently access remote memories. So that means with CXL support, we can actually make our memory space larger. So that will be very efficient for the memory bound application.
So any other questions from the audience? Okay, so if no more questions, let's thank our speaker again. So Linghao, thank you so much.
Thank you.
This very wonderful and very informative talk. And also thank everyone to join today's talk. So our next talk will be the 2 weeks later, next Thursday. Okay, thank you everyone. So see you 2 weeks later. Okay, thank you, Linghao. Have a wonderful day.
Thank you.
Bye.